All right, so what we're talking about today is going to be developing a theory, and we're going to be focusing on the plate tectonic theory that we have today. We're going to be starting back with Alfred Wegener and working our way into modern day. One of the things I want you guys to do while you're watching the video is please make sure you're taking notes. Make sure your notes are a summary, not word for word. So I want you guys to rephrase things in your own words, and you are welcome to pause the video. I am going to run through this very quickly. I will not cover everything that's on the slides, but you're welcome to pause and go back if you need to, but you're not writing things down word for word. I want you to summarize them. All right, so what we're starting with today is going to be Alfred Wegener in 1915. He was a scientist that studied lots of different things, and this was what allowed him to create, at that point, what we call the continental drift theory. And so he was saying that he saw some evidence as he was looking around libraries and traveling and different things like that. He stated several pieces of information. We're going to focus on three. He stated that the continents had a jigsaw fit. They seemed to fit well together. There was fossil evidence on multiple continents that stated that the continents should have at some point been together. And there was evidence from glacier activity. So areas where there were not glaciers at the time, there was evidence of glacier activity. And he presented this information through his continental drift theory. And so some of the things that he mentioned were jigsaw puzzle fit. He was able to put pieces of the continents together and show that they did fit together. We have a better understanding now that there is more to the continent than what we see on land. At the time, they had old maps, and maps were often drawn by people who were just sort of walking, either, walked along the shoreline or mostly got in boats. And as the ships were traveling along the shoreline, they would draw maps and things like that. So the maps were not the nice satellite images that we have today. And so he was able to still come up with this jigsaw puzzle fit piece of evidence to support his continental drift theory. He stated fossil evidence, so specifically the four main, if I click over here, it'll let me show you our Glossopteris right here. Our four main pieces of evidence, one was Cynonathus, and the Lystrosaurus. Both of these were late Triassic dinosaurs. They don't look like dinosaurs, but after the things that we think about when we think about dinosaurs, we think about Tyrannosaurus rex and Stegosaurus, but these are actually late dinosaurs, kind of what we believe most likely evolved into mammals. And so we have our Cynonathus, Lystrosaurus, Mesosaurus, which was an aquatic organism, but it was freshwater. So there was no way it would have been swimming across modern day South Africa to South America. And then we had Glossopteris, which was actually a plant. And we can look, the Glossopteris spread across 5 different continents. And so he said maybe this means that these organisms were not actually, maybe these continents were together more so than 2 land mammals, a freshwater creature, and a plant making it across entire oceans. Then he stated evidence for glaciers. So he liked to look at rocks. And so it would be one thing if we look up at this top picture, we could probably envision a sheet of ice covering this whole area. But he actually studied the way that the scratch marks that the glaciers left, the way that they left marks on the rocks. And what he discovered was that they were actually growing out. We were probably moving at this time into an ice age. They didn't know that at the time, but the glaciers were expanding away and moving into areas where modern day there would never be any ice. Even during the worst ice age, you're never going to have ice in sub-Saharan Africa. It's tropical. It just doesn't happen. This is their understanding of it. And so his way of describing it would be to say, well, then there must have been some sort of connection of these pieces, and that's because it explains the way that the rocks move kind of uniform to each other once we've rearranged the continents and not before. So a lot of things happened in between Alfred Wegener's posting of his theory of continental drift and the next time we had any evidence to support it. Alfred Wegener stated that he thought that the continents were indeed drifting through the ocean. So think about a boat moving through, and what it does is it's plowing water out of the way, or a train on tracks pushing, and anything that's in the way is going to get pushed off to the side. And so he used that analogy, and scientists at the time just really weren't having it. It was 47 years before there would have been any type of additional information. At this time, scientists are still studying the Earth. You had the end of World War I, the beginning of World War II, new creations, the first computer, microwaves, color TV. All of that is happening. Technology is improving. But it isn't until 1962 that somebody else makes a statement and says, look, I think that I can explain how these continents are starting to move. And Harry Hess came, and Harry Hess was a scientist who was drafted into the Navy, and he became the captain of a ship. And on that ship was a sonar, and he used the sonar to map the bottom of the ocean floor. And what he discovered in the middle of the Atlantic Ocean was what he called a mid-Atlantic ridge. And the mid-Atlantic ridge is a long mountain range that is constantly starting to put out new rock. So we have magma coming up from a magma chamber, becoming lava and flowing out. But it doesn't just flow over the top. What it does is it actually pushes through and it pushes out. And it's going to move that old rock out of the way, as allowing for new rock to come up and forming a new section of rock. So the Mid-Atlantic Ridge, while being a relatively tall mountain on the bottom of the seafloor, is not going to be this forever growing mountain. It's going to start pushing that stuff away, creating what you would have on the bottom of the seafloor, a long mountain range. And so what Harry Hess described was that this rock must be pushing it up, it must be pushing away, and what you would have is seafloor spreading. So it's basically pushing from this mid-Atlantic ridge, Africa and South America, away from each other, causing the seafloor to spread out, and thus the name seafloor spreading. At the same time as he was doing this research, we had other scientists who were taking up rocks from the seafloor and were using radioactive dating to get information about them. And they studied the orientation of the rocks, so which way that they laid, and what that meant for the minerals inside of them. Vine and Matthews were both geologists, very interested in the different types of minerals, and they looked at the magnetic properties of these rocks, these igneous rocks. And so that brought them to, look at this one, looking at this image. So here we have a model of our asthenosphere. So that's the top of our mantle. We have our crust. We have ocean layers over it. I'm going to go ahead and push play. We'll move through a little bit. And then what they discovered was they actually had striping of different polarity. And polarity tells us, we use polarity when we're talking about magnets. And so if you ever had a chance to play with magnets, you have a north side usually and a south side. So think about it, this is the north side and this is the south side over here. And so if you try to push the two north sides together, they're going to push apart. They don't want to get together. But if you flip over one of your sides and you have a south side, they're going to attract each other. This is polarity at its simplest. I'm trying to describe it quickly. And so we live in a time where magnetic polarity of Earth, so this is the orientation of Earth's magnetic field, is actually north, and it's relatively strong. So if we pick up a compass and we use it to discover where, let that arrow spin around, and it's going to eventually end up pointing to the magnetic north. What they discovered, what Vine and Matthews discovered, was that magnetic north was not always the case. Sometimes we had the main magnetic field actually would point south. And sometimes the magnetic field was so weak, we didn't really have a good direction. And so there would be a switch. There would be time where you could see that it was switching back to a magnetic north. So we currently live in a time that is very a strong magnetic north. But one of the things that we're discovering is that it is, in fact, starting to move a little bit more towards the south. So magnetic north is not as strong today as it would have been in 1915 or even in 1960s when Matthews and Vine were doing their studies. And so they took data from multiple parts along the sea floor, and they took collections from these different spots. Now remember, the seafloor is not nice and color-coded like this. It's probably a nice uniform, different color, lots of different rocks. We've got lots of igneous rocks underneath there. And so what they are going to be doing at this point is they're taking pieces equally, symmetrically from on the other side of the mid-Atlantic ridge, and they're radioactively dating them and finding out that not only do they have a matching polarity, but they also are similar in age. And so we have an even spreading out from the mid-Atlantic ridge. And this supported Harry Hess's theory of Harry Hess's observation that you have seafloor spreading on the ocean floor, pushing continents away. More information came by John Tuzo Wilson, and what John Tuzo Wilson was actually able to do was actually kind of fill in the gaps. Through seafloor spreading, it described that we had areas where new seafloor was being born at divergent plate boundaries, so where plates were moving away from each other. But we also had areas where seafloor was starting to be, and continents were actually starting to run into each other at convergent plate boundaries. And so what you end up with is we had two different types of boundaries, and we were able to describe how new rock was formed and how old was recycled back into the mantle, and explain why the Earth itself wasn't getting bigger and bigger. It was staying the same size. John Tuzo Wilson was not entirely sold, and he was trying to figure out, well, what about these areas where that's not happening? Clearly, plates are running into each other. There's movement, there's earthquakes, there's maybe even slight volcanic activity, or there's volcanic activity, but there isn't new plates being formed. And so he made two discoveries. One of those was that you have things like hotspots. So single spots in the middle of a plate that are pushing magma up through the ground, and they're going to create large islands in this case. And he discovered this while he was looking at Hawaii. And so what you have is here at the island of Hawaii, where you would have actual a new rock being formed. We have two very active volcanoes there now. And then you have over here at the very end of the island chain what would have been originally what was over the hot spot. So discovering this, he said there must be some kind of movement. And so he looked a little bit further, and what he found were transform boundaries. This was able to convince Tuzo Wilson that there were in fact plates that were shifting and moving. And he was able to put in that missing piece, finding that there are not just convergent plate boundaries and divergent plate boundaries, but that there are also these things called transform boundaries. And that's where you have plates that would move alongside of each other, transforming energy into large earthquakes and things like that, but not necessarily building or taking away from more of that land. So that information, he was convinced. And then we have a gentleman named Dan McKenzie. What he was able to tell us was we have two layers of in the mantle, and this allows for the sliding around of these plates. And he kind of put in that final piece that allowed scientists to really have a good theory, good solid theory. So I want you to take a moment, think about at what point would you have thought, this is a good theory, this is enough information. Thank you for listening.